So welcome to lecture 17 of the Mathematical Engineering of Deep Learning. I'm Yoni Nazarathy, as you know. So just some announcements before we move forward, and feel free to ask some questions as well. First of all, if you're looking at my image, there's you could see a sunset. Well, we have a virtual sunset behind me. It should set in about a minute or two, so I hope we'll be okay. So sorry about this lighting issue, but frankly, you're not missing much. So we are here in the middle of Unit 5. Basically, we have 50 minutes today. And then tomorrow, this is now the announcements of the day. Tomorrow, we have the third and last split practical. So you already know the drill for the split practical. You can go with Benoit for R, Sarat for Python, or with me for Julia, and go for the different Zoom links tomorrow. And tomorrow, immediately after the split practical, you have a lecture. So then you go back to the Zoom link, which is this one, the main course Zoom link with Benoit. Okay, so that's for Unit 6. And you already have the slides for Unit 6. So Benoit put them on, or we put them on. So go ahead and look at that. I must tell you that the course is now entering a phase where, in terms of your reading forward, you don't necessarily have to read prior to class, because now we're from tomorrow onwards with the tricks of the trade, and then moving on to the advanced units, the GAN, the sequential models, and the deep reinforcement learning. We're really going to give more of overview lectures on these things, also starting tomorrow. But of course, you're busy, so you've got a quiz this weekend, and you've seen the quiz summary, I assume. So you've got 2 questions on Unit 4 and 2 questions on Unit 5. And we'll send an email in the next day or two, or the next day, that will outline what to study for the quiz and what not. The quiz should be less time intensive, as we said before, and you're working on your assignment too. And also, you should already think about your project, because the checkpoint for the project is due pretty much just after we finish, right? So the project is due here on February 2nd, and the checkpoint is due February 8th. All right, let me just see if I can see the chat, because it disappeared from me. And there's some questions. Oh yeah, so the notes for Unit 6 are ready already. And there's a question where the papers to choose from the project. So when you go to references, and we'll actually spend just a bit of time on references today. So you've got a few things in the references section. So these key papers in the development of deep learning, they're not for the project. They're here because they're kind of key historical papers. I mean, key papers that where after each of these papers, it was kind of a significant jump, okay? Some of them are fundamental, some less fundamental, but they all kind of improve. This is kind of a historical perspective, okay? And then you've got these further deep learning resource learning papers. These papers are the ones that are for your project. Okay, so that's quite a collection of papers. Some of these are kind of very big famous papers as well, but spend a bit of time looking at these papers. Of course, you're not going to read all these papers. Just look at the abstracts and see what interests you, and also read the project description, and with that in view, choose the paper that interests you. Okay, I hope that helps. If there's a paper that's not on here that you'd really want to focus on for your project, send it to Sarat, Benoit, or to me, and we'll see, and it should probably be okay. Okay, as long as it's kind of similar to these or falls within our domain. All right, and slides are online, as Benoit just mentioned in the chat. No more questions? We get to business? All right, so let me change back to the iPad just so I could scratch on things a bit. Or you know what, if I'm here on the computer, let's very quickly. So what I'm going to do is I'm going to run this piece of code, and as it runs, so this, of course, you don't need to follow every little bit in this piece of code, but what it's doing is it's training these 2 models, Model 1 and Model 2, and we'll get back to speak about these models. So every dot that's being printed here is an epoch, okay? And there are 30 epochs, and it's training the models in parallel. So let's let it run. It's not going to take too long. Anyway, just if we're on the computer, might as well see it. And let's go back to the iPad and start to draw. So 1 second. Sorry. Success. All right. So a quick review. We've pretty much understood what convolutional neural networks are about. And we'll just spend a bit of time reviewing, and then we'll look at some of the further features we want to, some of the further items of convolutional neural networks. So we stopped pretty much here with a typical architecture. So just to get our head going, let me first ask you, I'll put the word there, depth. What is, I mean, in our course, in our context, and in what we're doing, what does depth mean? And it's a bit of a trick question because it can mean kind of two things. What does depth mean? Okay, so there is one answer, the number of layers, and we are in deep learning, depth, right? The number of layers. What does depth also mean? Right. And the second thing is the number of channels in an image, right? So the typical thing that we were dealing with was a network where we started maybe with a RGB image, so it had a depth of 3, and then we ran the first filter, and it could have had, it needed also to have a depth of 3 because the depth was 3, and maybe it was also a 3x3 filter. So too many 3s here. That's okay. But maybe we didn't just run one of these. We could have run 8 or 9 or 20, and then we would get an image, or sorry, a volume that would have a depth of 20. Okay, if there are 20 such filters, right? Where each channel here corresponds to the application of this filter on the original image, and then the story would continue to the next layer, next layer, and next layer, and then we might have some dense layers and finish with that. So we had here two architectures, and I think this is where we should pick up. So architecture one is, and again, this is Flux code. Your PyTorch or Keras or TensorFlow code or Caffe2 or whatever you want code will look slightly different, but this is in general the same type of thing, okay? So what we're doing is we're specifying a neural network. How many layers are in model 1? How many layers are in this neural network model 1, which is not convolutional? How many layers are in model 1? Okay, right. So there's 3. So there's, you know, a first dense layer, a hidden layer, a second dense layer, and a third layer on which the softmax operates, and it's also the output layer. Okay. Again, we got to be careful. Some people use, from a software perspective, some people might call this a layer as well, and also this a layer. Some people might even call the activation function a layer, but just when you're dealing with that, know what's meant, okay? But mathematically, we just call these the 3 layers. At least that's the notation we've used. All right, so there's this first question here, and we won't dwell on that, but you could just look at the answer. Well, how many parameters are in this guy? Okay, so the parameters in this dense network, so you've got 784 inputs, so it assumes a 28 by 28 input image. Okay, so that's 784. 784 got to 200 neurons. What's this 200 for? That I've just circled. What's this 700? That's a bias, exactly. And then we have the second layer and the third layer, and you get some number, and we have some typesetting issue here. That's just from copying into this software that I can scratch on, but 178,000 parameters. Okay. So that's this first model. But let's focus on the second one. Let's focus on model 2, which is of course convolutional. Okay. So model 2 has a first layer, which is a convolutional layer, and you could treat the neurons at the output of this layer. You might say that they're right here where I'm putting this line. Okay, so it's running 5 by 5 convolutions. Okay, so convolutions of 5 by 5. Remember, the convolutions would typically be 3 by 3, 5 by 5, 7 by 7, maybe 11 by 11. But humanity has gone to a smaller number of convolutions. We'll see that soon when we speak about architectures. Okay, and what does this 1 to 8 mean? Again, you don't have to know Flux or Julia per se, but we're going from This is operating on one input channel to 8 channels, right? So one, because this network is designed to work on a monochrome image and is creating 8 channels, it's going to do a relu activation for each one, and this is a default stride. And I see this disappeared from here. You'll see this on the website. It would also say padding equals 0, 0. Okay, no padding, and then max pooling. Okay, so let's already try to answer this question down here. What is the size of the output of the first layer in Model 2? Take your time. And by the way, the quiz will involve things of this type and a few more, but you know, they're not very deep questions, no pun intended, but just some questions. So what is the size of the output of the first layer in Model 2? So let's think. We're doing we're starting with a volume with images of 28 by 28. And when we're a square, all we care about is like, we can just think of the horizontal dimension, right? So we have this formula. I'll just write it up for you again. It's someplace up there. NX plus 2P minus NH divided by the stride plus 1. Okay. In our case, the stride is just 1, right? And P is 0, so 2P is 0. So it's basically NX minus NH plus 1. So I see an answer 24 times 24 times 8, but let's do NX minus NH. NX minus NH is plus 1. Okay, so is that the answer? Does somebody have something else? Oh, sorry. Yeah, this is 5. I think you're right. I take it back. I thought you were wrong, but nobody's correcting Jade, because I think Jade is correct. That's 28 minus 5 plus 1. That's 23 plus 1. I fully agree. I thought it was a 3-dimensional convolution. Okay, and that's what we get. Okay, so we got 24. Now, when you're implementing and certainly designing convolutional neural networks, you need to kind of keep in mind. So you can, some frameworks will do this for you automatically, but some won't. So you need to keep in mind that here you kind of put for yourself a note. You're saying, oh, I'm in 24 by 24 by 8. Okay, that's the volume. Now, knowing this is, by the way, also important. We've all the time spoken about the number of parameters of a neural network, but when we're speaking about big neural networks, it's also important to know how many neurons there are in the network. The number of parameters is certainly not the number of neurons. It's not the case for dense, fully connected neural networks, and it's not the case for convolutional, right? Because you're repeating things, right? This with the convolution. Why is it important to keep in mind from an implementation perspective the number of neurons? This is not a mathematical question, but an implementation question. Why would we care about the number of neurons? Memory requirements, exactly. So as you might know, some of the neural networks which we use, for example, if you use Siri or some other voice-activated system, etc., it's actually not implemented on your phone. This goes back to the server farm of the company, and they actually need to run a combination of several quite deep neural networks that have a lot of memory requirements. Okay, so the number of neurons is also important. So this thing, is this the number of parameters, what I've circled here, or the number of neurons? This thing that I'm kind of drawing on. Is this the number of parameters? It's a number of neurons. It's a number of neurons, right? So just keep in mind, number of neurons, number of parameters. So that's the memory size that you need if you're actually even using a pre-trained model, okay? All right, so we're there. Then we have a question. What is the size of the output of the second layer? So we're 24 by 8, and now we're doing 3 by 3 convolutions, and from the 8 channels, we're creating 16 channels. The other parameters are the same. Okay, there's a padding of 0. You can't see it, but there's a padding of 0. 0, 0. Yeah, meaning 0 on X, 0 on Y. So what do we have here? Oh, by the way, there was a mistake. So the 22 by 22 by 16. But I actually missed something. There was a bit of a mistake. I put 24 by 24 by 8. 24 by 24 by 8 follows from this formula. right? 28 minus 5 plus 1 equals 24. But what do we have here? I missed this. What do we have here? This is a max pooling. So what does this max pooling do? Does it give us 24 by 24 by 8? What do we get after the max pooling? Max pooling takes, exactly. So you're writing, so this is actually here before the max pooling. After the max pooling, we have 12 by 12 by 8. Okay. So max pooling took two adjacent pixel, well, every 4 adjacent pixels and took the maximum. Okay, so it cut the horizontal and the vertical dimension by 2. All right, and then here, what do we have then? So what do we have here, which is, what is the answer to the second layer? And so this was the answer to the first layer. What's the answer to the second layer? Okay, so with convolutions of 3, indeed, you're doing 12. You're doing 12 minus 3 plus 1, which yes, is 10, but you're also doing a max pooling. So what do you have after the max pooling? 5 by 5 by 16, exactly. Okay, so at this point, the input volume is not too big. Okay, of course, the input image was not too big either, but that's fine. All right, now, when you work with convolutional neural networks, just from an exercise perspective, but also from an implementation perspective, this number which you've got here, which is the number of neurons just before you're going to the next layer, is important. So this is size of volume, 5 times 5 times 16. Now, how is this related to this? What is this 400? Well, 5 times 5 is 20 times 16. We need to do it, but it's 400. Okay. Sorry, so 5 times 5 is 25. I mean, at least, okay, come on, 5 times 5 is not 20. So 16 times 25 is 400. All right, so the number of neurons which we have in the volume now gets flattened, just stretched out, and then we have our dense layer, that's 400. Okay, so there is no, if I was to go to the code, if I was to go to the code and change this 400 to be 300 or 401 or 399, it would not work because this number would not agree with this number. Okay, that's kind of the point. Does the number of neurons dense layer model have to be 400? Generally, yes. I mean, we say generally yes because we could have conceived some architecture where you don't have to have, you don't use all of them, for example. And how many parameters are in the model? Okay, so we spoke about layer sizes. Now let's speak about parameters. So first layer was 5 by 5 convolutions, so 5 by 5 filters, but not 5 by 5 by 1 filters. Okay, so we do 5 by 5 by 1 filters. But for each filter, we also get this +1. What's this +1 here? Yeah, so it's okay. If nobody else is answering, it's you. Yep, it's a bias. Thank you. All right. So, and then we multiply that by 8 because of the 8 of them. So 208 parameters. The second layer, we've got 3 by 3 filters, but times 8. What is this times 8? It's the number of channels we had from here, right? Coming into it. Okay, so it's the input volume depth, okay? And that's this number of parameters in the third layer, etc. This is now a dense layer, so that's a matrix W3. Okay, that's its dimension plus a bias, etc. So yeah, we have a much smaller number of parameters. 5,386 versus this 178,000. Okay, so let me quickly change back to these two models were trained while we were speaking. So I assume, can you see the desktop? Yep, thanks. All right, so there we go. It finished, and what we're doing, you could find this code in GitHub. We'll also tomorrow in the in the practicals, you'll do PyTorch and Keras with Sarat, and you'll do Keras with Benoit, and on the respective languages, you'll do Flux with me. You can see more of that. But basically, it did training with cross entropy loss and ran 2 atom optimizers. So it trained in parallel on the same mini batches, right? So in the training loop, in this for loop, it did train the first model, train model 1, and train model 2. Okay, kind of in each one. Okay. And it trained actually on a small data size, so only 5,000 observations for the training from MNIST, and 5,000 for the validation. And what you can see here, this is not the typical plot where on the horizontal axis we put the batch number. So that's what we did. It's not the typical plot where we do the number of epochs. Okay, just to get kind of a bit of finer granularity in the plot. What you can see is that the convolutional neural network is more effective. I mean, come on, the convolutional neural network had 5,000 parameters, whereas the deep neural network had, sorry, not the deep, but the fully connected network had 178,000. Okay, and the 5,000 parameters use the fact that they were convolutional. So since this is an image looking at things locally, etc., was useful and the right thing to do. So convolutional neural networks are strong. Questions so far? All right. So now let's look. If you remember, I've shown you, it's also in this Julia notebook I've just shown you, but I've shown you in the previous lecture, but also I think in lecture number 1 or maybe lecture number 2, I think it was lecture number 2 of the course, using a quote unquote industrial strength architecture. Okay, industrial strength architecture. In this case, it's the VGG19 architecture. Okay. Trained on the Imagenet database. Okay, so the Imagenet database was kind of the main collection of high-resolution color images that was created around around 2008, 2009, and since then the Imagenet challenge kind of moved forward, and that really drove deep learning research. And this VGG network from 2 researchers in Oxford, we'll actually see the paper just a bit later today, was came out in 2014. It wasn't the seminal paper. It wasn't the most important, but it actually did very well on the challenges. So it's good to see it. Okay, so what we do in this code is we actually download the pre-trained network, meaning that we download both the network architecture and all of the parameters. This is not something I would train on my laptop, okay, or you on yours. It would require GPUs and a lot of compute time. Okay, so the network is pre-trained, and as you'll hear from Benoit tomorrow and Friday, one often uses pre-trained networks in transfer learning. So you use a pre-trained network, and then you take the dense layers at the end, and you retrain those on your specific data, but the convolutional layers that were pre-trained before are already in quite good shape. And what we're seeing here is just this little loop prints the network architecture for us. Okay, so it's in a sense the same software representation that we had here under all this mess and scratch, but this is not code, this is output, that's architecture. Okay, so we see this network is very standard, and it fits exactly the paradigm that we spoke about. We start with 3x3 convolutions with 3 input channels. Why are there 3 input channels in this case? Before there was 1 input channel. Okay, RGB, perfect, right? So that's a RGB. Now let me just pause for a second and answer a question I see in the chat. It says in the footnote of the flux code for the CNN, it says there's a second layer has 16 filtered X creates 16 channels. The second footnote, maybe here. That dollar is a typo. Sorry about the typo. The question is, yeah, okay, it's a formatting error. Sorry. Trying to put 16 in LaTeX and not closing it. Okay, sorry about that. Okay, thanks for pointing that out. Okay, so you've got RGB, and then we go to 64 channels, right? And then from 64 channels, we stay at 64 channels, run another convolutional layer. After these two layers, we do max pooling, so we cut the input size. Now the input size, I believe, is, we'll see at the bottom, is 224. Yeah, 224. So if you wanted to, and it's maybe a good idea as an exercise, you'd start here, you do 24. So here, for example, you do 224 minus 3 plus 1 is 200, I guess, 21, 222, right? So there's no padding. So you've got 222 by 222, okay? And then you do the same type of thing here. So then it's 222 minus 3 plus 1 is what, 219, 220 by 220? 220 by 220. And then after the max pooling, one can do padding on max pooling, but there's no padding in this case. You get 110 by 110. Okay. So what do you do? What does this code in this specific package Metalhead that we've used before do if you give it an image that's not 224 by 224? Well, it does its best effort outside of the neural network to downsample it just to 224 by 224. Okay. One way would just be to do kind of this quasi max pooling to get it in the right dimension, but it can do different things. Okay. So now you can understand this. You've got convolutional layers, convolutional layers, convolutional layers, convolutional layers with occasional max pooling. Then you've got this funny thing. This is just a reshape. Okay, that's just a reshape. So why do we reshape? So one can actually calculate that at this point, the number of neurons in the volume given 224 inputs, 224 by 224 inputs, is 25,088. Okay, so I'm just saying in principle, it's not so difficult, or you could also do it with a bit of software. With this input and with this architecture, you know that you've got this size of volume, and this 4,096 is kind of arbitrary. Well, it's also, these numbers are often picked based on GPU architectures, because these are kind of numbers that sort of fit in architecture. So often using powers of 2 kind of makes sense. Okay, you see everything is kind of powers of 2. 4,096 is 2 to the power 12. Okay. What are these two layers here? Well, they're not layers, they're elements in the network. So that's dropout. Okay, so the network has dropout here and here in the dense layers. As I said, we don't do dropout typically in the convolutional layers. Okay. And when you hear from Benoit tomorrow or the next day about transfer learning, I'll just say it in a word here just to steal a bit from Benoit. So basically that means that you've got this thing that's pre-trained, okay? And then you've put different inputs, okay, which are not the Imagenet inputs. Maybe they're just images of your friends or something like that. And you retrain these parameters, okay? You retrain these parameters. That's one variant of it. And you see the feature maps, which you have here in the last convolutional layers, are already kind of this AI. Of course, this is not AI, but that's what people kind of call AI, okay? Or whatever, that know how to recognize features. All right. So when we train CNNs, there's not a lot of content here, but basically mathematically training a CNN is using the same forward pass and backward pass that you do for fully connected networks that you learned about with Benoit in chapter 4 in unit 4. But the thing is that you only train the parameters of the filters and their bias terms. GPUs play a key role. Okay. All right. There's a question. The dropout will affect the following layer. Yeah, so the dropout, first of all, plays a role in the training. Okay, so it's an element in the training where in every run of a mini batch, you flip a coin, in this case, really a fair coin, and you say, are you going to train a neuron, yes or no? And depending on how the dropout is implemented, sometimes you then renormalize by that dropout quantity. So you divide by 0.5, which is like multiplying by 2 just to keep everything in scale. Yeah. So, and yeah, it will affect the previous layer in flux, but that's a software question. Okay. So dropouts on the previous layer. It's not the following layer, it's a previous layer. Okay. So this dropout is for this and this dropout is for that. Okay, let's move on to the 4 famous architectures. Now you can't see the videos here just because this is kind of the software for scratching on downloaded websites, but so you see it here. Yeah, so you could watch this about GPUs, by the way. It just gives a bit of a feel to what it's like to program a GPU. But just to be clear, you're finishing this course, you're not still a machine learning professional, but you can now maybe train yourself to do more things with TensorFlow or PyTorch or Flux, probably not with Keras, because Keras is more of a kind of a high level thing. And then, you can kind of claim, hey, I'm getting to be a machine learning professional. Now, when you do that, you don't actually need to program a GPU as in thinking what's happening in the GPU, and that's what you see in this video by Siraj Raval, okay? But you just need to interface with the GPU properly, okay? Still, this video gives you kind of a feel to what's in that GPU. Now, I'll spend now just a few minutes on speaking about the 4 famous architectures, and we'll also look at a few papers. But I also recommend watching this full lecture. It's part of a course in Stanford that focuses on convolutional neural networks. That course does not have the same mathematical focus we have, but it's a pretty good course. It's a very good course. So that whole lecture, that's a 1-hour lecture, kind of goes into depth into those 4 architectures. Okay, so what are these 4? And keep in mind, throughout this course, we didn't have much of a historical perspective, but we'll take this chance to do it now. So we're looking at the references for a second. And all these 4 architectures are here in the key papers in the development of deep learning. Now, I must say that some of the things done in these papers are it's not, I mean, these are great papers, etc. But it's compared to some other papers in the key papers in development of deep learning, this is not kind of cutting edge, fundamental, unique ideas. Yeah, it's not like the invention of the fast Fourier transform or something like that. But these 4 papers just had an incredible influence on deep learning. So this first paper that's not in the 4 architectures that you see at the top of the page, that's in 1998. This is really the first. 1998 is a long while ago, at least from the context of deep learning. That's a paper that really had convolutional neural networks roughly as we know them today. And it worked pretty good for image recognition, but this was still didn't beat any competitions. Imagenet did not exist in 1998, but it didn't blow people away. There was also a period in the 70s and 80s, which was called AI winter, where some of the early ideas from the 50s and 60s of the perceptron and things like that. So deep learning was really invented in the 60s in a paper not here after the perceptron, but there was kind of a thought that this thing won't work well. But all I want to say is that this paper from 1998 by Jan LeCun and many others that have made impact on the field really had the initial convolutional neural network. I guess we're not going to see it. That one is not directly to a PDF. Okay, but the first of the 4 architectures that we will speak about just for a minute or two appeared in 2012, and it blew away the ImageNet competition. That's this paper that's later became known as AlexNet, named after the first author. Now, I want to say that these 4 architectures that we're going to see, out of them, only one really fits in the exact paradigm that I've taught you in the past 2.5 hours, which is how convolutional layers are working on volumes. So the 3 other papers, and this is one of the 3 other papers, actually have a bit of a twist. So they don't fully fit in this paradigm of convolutional layers straight up clean as we've spoken about them, potentially with max pooling. You can guess which one does fit in the paradigm, just because we've looked at it. So which of the 4 architectures fits exactly in the paradigm? And by the paradigm, I mean, we've got, VGG. So we've got volumes, convolutions, max pooling, etc. No shticks, no tricks. Okay, so VGG is actually exactly that. All right, just something to keep in mind. Okay, because VGG we can kind of fully understand according to the framework. But let's look very briefly at the AlexNet paper. AlexNet, up to a few years ago, it was perhaps used for some things. Today, it's been superseded by VGG, Inception, Resonance, and the like. So the main point to see is to kind of look at the architecture here in the paper. And we don't have to go into every bit of detail, but at this point, you know what a convolutional network stands for. Now, there's a question, does VGG stand for something? Yes, it does. I forgot what it is. I don't know the answer at the moment. Maybe somebody can answer. All right, so we're working on input images. What's just looking at this image now, input image is 224 by 224, as you can see. What's the size of the first convolution, the first kernel? What's the size of the first convolution? In AlexNet, 11 by 11. So that by today's standard is quite a big convolution. Okay, now and then there's 5 by 5 convolutions and 3 by 3 convolutions. So there's about 10 layers or so. Now the thing is, this paper and this framework, this network was trained and then won the competition, etc. Before the days of Keras, Flux, PyTorch, and even TensorFlow. Okay, some prior frameworks existed, but there was no framework that's as easy as today that we're just coding, and you're going to do this tomorrow in the practical that just kind of goes and codes things. And actually, things had to be hand programmed in C, etc. But there are also these two parallel tracks. There's this bottom track, which you see in the top track. So you can see in the top of the image now, the top track, it's kind of truncated in the image there, but that's just the way the illustration is presented in the bottom track. And what's happening is there's kind of splitting of the volumes into two parallel streams, kind of like two eyes, if you would like, okay? And then reconnection of them towards the end here with the dense layers. Okay, towards the end with the dense layers. Okay, this was for computational reasons because this was just trained on 2 GPUs that existed at the time. So a lot of the art of making this work had to do with good engineering and good computation, etc. Okay, now you could see here by this layer here that has 192. Then there's by the layer after the second max pooling. Then there's communication between the two GPU streams. But what I want to say is that this architecture is already kind of breaks the standard paradigm that we've seen that VGG doesn't. Okay. All right. So that's AlexNet. Let's move to the next one. Of course, you can read more about AlexNet, etc. But the point is, it was historically it was like just a great architecture that really kind of awoke everybody and said, "Oh, wow, deep learning grid can really work." Okay, so the next step after AlexNet, well, in 2014 there was actually the Inception Network, which is our third one, okay, or called GoogleNet, but has Inception modules, but VGG. So we've already looked in detail at the VGG network here, or in some detail. Okay, this is an illustration of VGG. Okay. Now this is a chance for us to just introduce some idea. It's called the receptive field. Okay, so the receptive field. So let me actually move to this thing I can scratch on, and we'll speak for a second about the receptive field. So the receptive field of a neuron. Okay. Whoops, sorry. The receptive field. All right. So there's kind of an architecture consideration to think of. If you're here, and this, let's say this is the original image. What I have here on the left is the original image. Okay, and then you go through some network bits, and then you're on one neuron here. Okay, on which there have been a few convolutional elements. So this is a neuron, and this is the original image. Okay, The receptive field, we don't have to speak about a neuron and just the original image. We can speak about any image back. Right? So there's for every neuron you'd be interested, what part of the original image mapped to that neuron. Okay, I mean, we should hope that if this neuron is here towards the end of the network, all parts of the original image map to it, right? But you know, when you're here in this is now the original images would be here, 224 by 224 by 3, okay, and then it goes into this type of thing, okay, 224 by 224 by 64. All right, so it did a 3 by 3 convolution, right? So a 3 by 3 convolution here for this neuron, all you're covering is an area of 3 by 3. Right? Now, it turns out, and it's very easy to see, that if you take, for example, this is a neuron, and then you say, I've got a 3 by 3 convolution. So just before that, you covered 3 pixels. And then this one here, it was based on a previous 3 by 3 convolution. Okay, so it was also based on a 3 by 3 convolution. So, and this one was based on a 3 by 3 convolution, and this one was based on a 3 by 3 convolution. All right? And let's even go one more, and then you've got a 3 by 3, and a 3 by 3, and a 3 by 3, and a 3 by 3, 3 by 3, 3 by 3, da, 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 da. Okay, so you go and you ask yourself, oh, what's a receptive field after you've cascaded 3 by 3 convolutions? Okay, and what you'll get is that it's 7. It's a receptive field of size 7. Okay, so you just get it because, you know, from the first 3, you just then cover one more, so you get from 3 by 3, you then cover a receptive field of 5, and then you cover 2 more, and then you get to a receptive field of 7. So then one can consider architecturally and say, hey, I can do the AlexNet thing, which let's take here, for example, I can go with very big convolutions here of 11 by 11, okay? And the thing is that this neuron has a receptive field of size 11. Right? It covers this neuron here already is based on an 11 by 11 chunk of the original image. So you can do that. Or I can break this up and I can do a 3 by 3 followed by a 3 by 3 with no max pooling or anything, followed by a 3 by 3, followed by a 3 by 3. Okay. Now, these are not the same things. An 11 by 11 is not exactly like doing these 3 by 3, 3 by 3, 3 by 3, 3 by 3. Sorry, and then I'll need one more, followed by 3 by 3. Okay. But the receptive field of this combination of 5 convolutions, one after another, versus this one, which is just a single convolution, is the same. Now, that architectural consideration drove people that did the VGG to actually go with a rather standard architecture and just say, okay, let's just go for smaller convolutions and go a bit deeper. Okay, a bit. So there's VGG 16 with 16 layers, VGG 19 with 19 layers, and this is preferable. Now, this thing is preferable because if you just compute the number of parameters and you've got 9 per channel, okay, let's just assume a single channel. So that's 9 times 5, which is 45 parameters, and this is 121 parameters. Okay, that's a type. So these receptive field arguments, and you can dig more into them. The key point here is that we use this as like a case to see the receptive field. You can also read a bit more about this in this blog post, but it's not so critical. It was kind of an architectural consideration of going into to do smaller convolutions. So you see we've got here, it's all 3 by 3 convolutions in VGG 19, all 3 by 3 convolutions, as VGG 16 and 19. The 16 and 19 were just 2 variants, okay? All are 3 by 3 convolutions. And the receptive field is, these are designed such that you've got 4 3 by 3 convolutions. So you've got a receptive field of 9. You've got a receptive field of 5. A receptive field, I mean, from the previous layer. A receptive field of 9 again, etc. And after them, you put max pooling. Okay. I hope that's kind of clear. These are very heuristic arguments, but these were, this is the type of thing that's been happening in the field, and good engineering with good heuristic arguments kind of made things work. Okay, so that was VGG. Let's go to the third paper and model, which is really today used by a whole lot of things. I think even VGG, I know VGG is used less, but Inception is what you would really use in practice, okay? And that's the 2014 paper here, or 2015, that's the years 2014, 15 are not so clear because it's when the paper appeared and when it was published, etc. But that's the Inception Network, also called the Google Net. Okay. So the main idea of this network, they actually reduce the number of parameters significantly. Okay, so I won't speak immediately on numbers. You can see a lot of this in this lecture that's up here, kind of number quantification. But again, we care about the RAM size, we care about the number of parameters, and we care about performance as a function of number of parameters, right? I mean, if you can cut your number of parameters by an order of 10, but only degrade performance a bit, that's a great thing. So the key idea of the Inception network is this thing called an Inception Module. And I'll actually show you we can't see it on the, sorry, I'm jumping between things here. But an Inception Module is one part of an Inception network, also called the Google network, and these things are cascaded one after another. And Google did a whole lot of optimizations because they had a compute power on the validation set, obviously, to choose what they thought was the best architecture. And since then, there have been several versions of Inception. So I just changed back to this page so we could see what this YouTube video looks like. So I'm not going to play it, but you could watch it, like a 1.5 minute YouTube video, and it shows what an Inception module is. Now, let me just explain the idea. The idea is simple. The idea is when we're now going from, quote, layer n to layer n plus 1, we're not just going to do 3x3 convolution or 1x1 convolution, or even just a no convolution, just max pooling. We'll do all of them together. Okay. Again, in these architectures, we're deviating from the standard architecture that actually VGG lives by. Okay. So what we're going to do is, you can see in this image, you can see there's going to be a 1x1 convolution. Again, 1x1 convolution goes through all the depth, so it's useful. Okay, it's not just nothing. There's going to be a 3x3 convolution, and there's going to be a 5x5 convolution. And then what's going to happen is they're going to be concatenated, stuck together into one big thing. But to keep the dimension the same, there's going to be another 1x1 convolution that would kind of keep the number of neurons the same. So the Inception network, also called Google Net, and there's several versions of this network since 2014, 2015, is a cascading of one of these modules after the other, after the other, after the other, after the other. And it allowed first to keep a relatively small number of parameters, okay? And to also maintain kind of a constant parameter size, as opposed to, say, the VGG style net, where you're kind of going down in the number of parameters, right? So you see that you're kind of going down in the dimension, in the XY dimension, the width height dimension, and then you're making the depth dimension bigger. Okay, and it turned out that this thing just rocked, okay, and did wonderfully. So that was Inception. I see it's 4:50 already. I think I'm speaking a bit too slow. I'm going to steal another 3-4 minutes if you don't mind. Okay. So the final module, the final, say, major architecture is called the ResNet, the residual network. Okay, since we did this for all the others, let's not neglect the ResNet paper. So you'll see ResNet. And of course, there's a video on there as well. So with ResNet, here's a 2015 ResNet. With the ResNet networks, we could go much, much, much deeper. So we're talking about 150 layers and things of this order. Okay, and today they're deeper, but 2015, 150 layers was a lot. Okay, so remember, AlexNet was around 12, 10 layers, VGG 16, 19, 16, 19 layers. This is not clicking, but that's okay. And then 150 layers. Now, the key idea there is to actually skip from previous layers. So this is kind of the one thing to keep in mind. So we're going to, per layer, we're going to do these kind of skips. So you see, you skip from one layer, you're skipping from what you had 2 layers before that. You're doing these skip connections, okay? And there's a whole bunch of justification for why these skip connections work. But what's basically happening is you're avoiding numerical issues that would otherwise happen with very, very deep networks where your parameters just won't converge. Okay, these are not issues of overtraining of too many parameters, but just issues of too much depth, and then the forward propagation, backward propagation, you have vanishing gradients and things like that. Okay, so today's state of the art, so that was ResNet in just a second, but today's state of the art is really a combination, by the way, of Inception and ResNet. Okay, and just so you know. All right, so these are kind of, each one of these networks had a different idea, except for maybe VGG, which is, you know, the idea that we spoke about throughout. Okay, but of course it's useful as well. Okay, I'll skip this bit on inner layer interpretation. You might speak about this with Benoit just a bit. I'm not sure if you'll have time, but it might appear. And the thing is that there's a whole bunch of an attempt to interpret what the meaning is of the learned parameters of a deep neural network. The sad fact is that we don't know yet. Okay, and these models are not necessarily, are just not interpretable. So linear regression and generalized linear models are very interpretable. So if you know that beta 7 in a linear model is 25, you know that when you increase x7 by 1, your y increases by 25, for example. Okay, but that's not the case in deep neural networks. Still, this video that you have here is worth watching. Again, this is outside the material. And the last thing I want to speak about very, very quickly are all these things that you'll find with convolutional neural networks that are not just classification. Okay, so I mean, the first image task we have is, hey, here's an image, let's classify it. But there are many other questions: localization, landmark detection, detection in general, etc., etc. And I'm just going to focus very briefly just on the simplest one, just so we get a feel for it. Okay. And if you want to learn more, it's in one of the other deep learning courses that focus on applications. You've got that in Deep Learning AI from Andrew Ng. It's wonderful. You've got in Fast AI, etc. But it goes kind of away from the mathematics of deep learning. So here's object localization. Bird in the sky or stork or something like that, but let's just call it bird in the sky. Okay. So when you see this, maybe at first this is the simplest of these tasks, and that's the only thing we'll do. The question is, 1, what is it? Is it a bird? Is it a plane? Is it Superman? Or is it nothing? Okay, no, bird, plane, or nothing. So that's kind of the bird, plane, or nothing. That's the first question. Okay. The second one is, where is it? So one way to define where it is to say, okay, it's at the top. There's this XY, these two XYs, which are kind of according to this picture. Yeah, this would be, say, the X, and this is the Y. Okay, the coordinate of the top left corner, and then the height and the width. So you put a bounding box about it and class bird. Okay, so when we speak about localization, we're speaking about localization plus classification. Now, the thing is, and we put this here just so you see that it's simple, it's actually not so hard to to train such things if you have trained data where you actually have bounding boxes. Okay, if you so if you had image data that had both the classes and the bounding boxes, it's not so hard to train. So one way to do this would be to have the output label to be this kind of 7 vector, okay, where PC would be the probability of is there something or not, okay, is it nothing or not, okay. Of course, in the training data, it'll be 0 or 1, but in the output of your network, it'll be a probability somewhere in the range 0 to 1. And then you've got your for tuple, which describes the bounding box. And then you've got the probability of class 1, yeah, bird, and probability of class 2, plane. Okay. So then, like for an image that has nothing, if the image was just blue sky without this guy, all right, it has nothing, the input label of the training data would be a 0 and then a whole bunch of don't cares. I mean, it doesn't matter what we put there. Okay. And if the image had, if it was like this image, for example, then we'd exactly put these values. And we'd put, like for bird, we'd put, you know, we'd put here a 1, the X, Y, height, W, and then we put a 1 and a 0. That's for P1 and P2, because it's not a plane. It's with probability 1, it's a bird. And then at the output of the network, you both have softmax to classify the class, but you also just read the outputs X, Y, H, W. Okay, that's, you actually have it. So you're doing classification and regression together. And then one way in which you might implement your loss function, you can do it better with a cross entropy loss, but just for simplicity, is then for a network that outputs a label y hat, okay, a label vector, the 7-dimensional y hat, if the actual label was 0, if there was nothing, then all you care about is the first coordinate. That's a PC. Yeah, so that's PC hat minus PC squared. Of course, you can do a cross entropy loss here. It might be better, but that's okay like that. And if alternatively you actually had something, okay, if y was 1, this y is like PC and PC. That's this y is a PC, if there is something or not, okay. Then what you're going to do is you're just going to do the sum of squares difference between what you got and what's there. All right, so you can stick this in a network. It's even an exercise you could do. You might take MNIST images, go from 28 to 28, put them in like 100 to 100, put them randomly. So actually, you know how you create your data, train a 100 by 100 network to output these in tuples. Okay, if it's MNIST and you want to only have 2 categories, you'll have 10. And then this thing works. But this is just the first step for kind of things that are beyond classification. Whereas if you look at this video by Sarat Raval speaking about YOLO, for example, that's maybe kind of the state of the art. Now, just a question, is the concept of bounding boxes somehow related to I'm not a robot checker, where we select cells of image containing a stoplight, for example? Yes, it is. And it's actually, in certain cases, when we select that, we've been the slaves of creating training data for Amazon, Mechanical Turk, and the like. And well, good slaves or bad slaves, I don't know, but we created good data sets. Okay, other questions? Sorry, I went a bit over time. Nope.
I had a question about the assignment.
Yeah.
So, sorry, just let me pull up the specific sentence. So right at the start of question 1, come back, darling. It says, blah, blah, blah. In this question, you will implement the training of a 2-layer network from first principles without using a library such as Keras.
Yeah.
The first time I read this, I thought it meant you are going to build a neural network from scratch. Then I started doing that, went back, read it, and thought, no, they're just saying you train it from scratch. So do I build the network that I train, or do I just, like, can I use Keras to pull out to make layers and I build the network that way and then train it?
Yeah, no. So the purpose of this question is to really explore the equations of the forward pass and then the back propagation with the chain rule, the backward mode automatic differentiation manually. So no Keras, no Flux, no PyTorch, no Caffe, no TensorFlow. Okay. You don't have to do it in assembler. You can use Python or R or Julia. Okay. So, but first principles, you know, if, for, while.
Okay.
Yeah. Okay.
All right. Yeah.
So it's one of the, so yeah, it's just 2 layers, but this can take a bit of time. It can be fiddly, but it's one of those things that after you do it, if after you do this question, you know, whenever you use a framework, you'll know, oh, okay, that's kind of what's happening in the back end.
Okay. Awesome. Cool. Thank you.
No worries. Oh, and yeah, there's a question like NumPy. Yes, you can use NumPy. I mean, yeah. So again, I was like saying assembler. Yeah, you don't have to do it in assembly. Okay. No. Okay. You can only use a solder iron and a 24-volt battery and connect to that. And yeah, see you in a year. No, I'm joking. So like that's what they did in the perceptron. They were connecting wires. A year. No. Yeah, you can use NumPy. Okay. So just don't use a framework. NumPy is part of Python because Python doesn't have vector operations without NumPy. It only has lists, which are inefficient. Use Julia. No, you don't have to. Other questions? All right. So tomorrow, practical, split practical, Julia propaganda. Yes. A bit of propaganda never hurts. Split practical, BL, SMYN. You've got it here. Get it running before. For example, if you go to Charts, you've got the Google Colab one. And yeah, I think we should finish. Time to go. For you guys in Sydney, it's late. All right. Bye, everybody. Okay, just one last question. Does it work? Let's see how many people show up in Yoni's class tomorrow. Okay, see you. Bye-bye.